scared me to death. Vika!
Okay. Can you come here, right? All right. Yeah. So I'm Vikas Bhandawat, and I'll start by introducing our team: Gabriel Antoniak, Chanwoo Chun, and Tirthabir Biswas, and myself, Vikas Bhandawat. And what we are going to do is, I and Tirthabir are going to sort of summarize the work, and then there are two posters right outside, if you want to go into this in more detail, right? All right. So yes. Essentially, I am a neuroscientist, and I myself sort of backed into this problem when we started studying the neural control of fly's locomotion, and realized that the center of mass kinematics of the fly is relatively simple, and one should be able to understand those kinematics using simple mechanical model. And as you all know, sort of the classic example of such a mechanical model is slip, where you have a single effective leg that can describe both the center of mass kinematics as well as the pattern of ground reaction forces for many different runners that use different number of legs, for example, right? And so essentially our thoughts were sort of inspired by slip, and sort of the long-term goal is to try to develop a simple model in the spirit of slip that can explain locomotion across all gaits and speeds. And what we will do today is talk about the progress we have made in developing a model for the center of mass kinematics and dynamics over the entire range of walking speeds. And so specifically, we want to do three things. One is use in recent years, slip has been used not only for running, but also for walking. And what we want to do, first of all, is show, using non-dimensional analysis, that slip is rather limited in its ability to model walking. And then we want to show that a simple extension to slip is able to sort of improve the performance of slip at modeling walking. And finally, we are going to compare slip and AR slip, the ability of slip and AR slip, which is our new model, to model fruit fly and human walking. And so I'll start by sort of saying why we pursued fruit fly and humans in parallel. So a couple of the reasons are quite obvious. There is a large difference in size of these two animals, and there is a large difference in the number of legs, therefore sort of helping to probe how general a model is. The more important difference between these two animals is that they walk at very different walking speeds. So each dot here is a single step, and what you can see, and so these are our data, but it's generalizable across other people's data set. Flies limit themselves to very, very low Froude numbers, and humans use slightly larger Froude numbers, and together they allow us to scan the sort of entire range over which animals generally use walking. There's another really important reason, but before I get to that, I will have to introduce you to our sort of experimental paradigms. So in terms of humans, it's all standard stuff that data that we got from our collaborators, using the Vikan systems and 47 markers to get the position of the center of mass and of different limbs, and then use the BATEC force plates to get the ground reaction forces as the subject is walking. For flies, we created this kind of arena where the fly is walking on a curved slip. We are imaging the fly from the side view here, as well as there is a mirror that gives us the bottom reflected view of the fly. Here is a video to see how this looks. So essentially, what we get, our data set is essentially the center of mass position in X, Y, and Z. And the important point I want to make is that you can see this nice bumps, which really illustrate that we have enough sort of spatial resolution to understand sort of the kinematics of center of mass. So in the case of fly, what we have is the center of mass kinematics, as well as the position of the leg tip that helps us to define the gait of the fly. And it turns out that the flies across the entire range of speed basically predominantly use a tripod gait, where the front leg, the back leg of one side, and the middle leg of the other side form a tripod base of support. These tripods alternate between the one side to the next. And as you can see, that this gait essentially looks like a bipedal gait if you think of the three legs as a single leg of a biped. So now that we know how to define a fly stance, what I'm going to show you next is how the pattern of the height of the center of mass and the velocity of the center of mass as a function of the stance cycle. And this is shown here. You must all be familiar with this. In the case of human walking, the center of mass increases in height at mid-stance, and the velocity of the center of mass decreases at mid-stance, and this is the famous sort of cycling between the potential energy and kinetic energy that is described for walking. Now, if you look at fly, if you look at the center of mass height, by and large, they also increase the height, although there are steps where they do decrease the height, even at slow speeds. Now, interestingly and strikingly, the speed of the center of mass always reaches a maximum at mid-stance in comparison to humans, which has the opposite trend. All right, so that's the second reason we used fly, is because I think if you're trying to make a general model for all animals, I think it's important to capture the diversity that you see in the natural world. And with that, so the bottom line, the basic approach we have is we have, based on the fly and the human, we have come up with sort of features, general features of locomotion that most walking animals satisfy, and we will ask how our model does, how different models perform and explaining those features. So the first feature we use is what we call the height ratio. That is, how much height does the animal change during a step. And you can see that for human, it is in a very tight bound, and so it is also for fly. And we think that any model should satisfy the height ratio that is between 0.9 to 1.1 or 10% on each side of the normal uncompressed height. Then the other parameter we have is what we call the gait parameter, and this is meant to describe the different patterns of velocity. So the flies, by and large, because they have mid-stance maxima, they are below 1. Humans, mid-stance minima, so they are above 1. And all of them are still within a reasonable range of the average speed during that step. Finally, for mammalian walkers in particular, it's really important that they have this vertical, M-shaped vertical ground reaction force. And again, a model should be able to generate this kind of force. And finally, the minimum in a single stance phase should not get uncomfortably low. And we ensure that by keeping the bounds as 30% of the body weight. So essentially, I'll hand it over to Tirtho now, and he'll start by asking how well does slip do at basically being able to generate trajectories with these constraints?
Great. Thanks, Vikas. So as Vikas mentioned, our strategy is to characterize realistic gaits, walking patterns, and then use that to constrain the parameter spaces of any given model. So what you see here is an analysis for slip. And so we use dimensionless variables. We have 4 for a symmetric slip. This is the angular speed at mid-stance. This is the spring constant. And this is the alpha, which is the angular amplitude. And for the purpose of illustration, we are keeping one quantity fixed, which is the leg length at mid-stance over the natural length of the spring to be 0.95, which is typically a number that we get for our human fits. So what you see here is, so these colored regions are all the allowed gait space, which means these are the only regions in parameters which satisfy the constraints on height and speed variations that Vikas mentioned earlier. All the other regions are essentially excluded. And now if you focus on within this colored region, what you see is as you specifically increase alpha, slip has a challenge. It's unable to model really slow speeds, okay? So for instance, let's look at something like 20 degree or 25 degree, which is relevant for humans. If you look here, it's kind of just bluish, which lands somewhere here about 0.15 or so. Now, if you decrease alpha, it becomes easier for the animal to maintain relatively uniform motion, so it can do better. So something like 10 degrees, which is relevant for fruit flies over here, is, you're reaching the dark blue part. It's somewhere here, about 0.05 or so. All right? And let's see that more clearly in this plot. So if you look at this plot here, we are just looking at the range of the Froude number possible for slip, which is this middle region over here, as we vary alpha. Okay? So the way we do it is for a given alpha, we vary over all the other dimensionless parameters to get the minimum points as well as the maximum points. And as you see, for something like 10, 11 degrees, we get to about 0.05. This is obviously a log scale. And for about 25 degree, we get to, maybe a little hard to see, it's close to 0.15 or so. So clearly there is, slip has a problem in ensuring slow, relatively uniform walks. Yes. Yeah, it's basically just the V square over GR. So V is the speed, average speed, G is acceleration constant, and R is the, let's say, the leg length, average leg length. Okay, so it's just a measure of speed. Yeah, it's basically a dimensionless speed. And we use dimensionless quantities. First of all, it reduces the number of variables, and also it makes the analysis as species independent as possible. Yeah, I should have mentioned that. All right, so this is essentially a result that for the kind of alpha that we see, we don't walk like 1 degree or 2 degree if you want to walk slowly. We do maintain a certain alpha. So for those realistic alphas, it's hard to go below FR of 0.05 within slip. So it's easy to see, intuitively understand why that is the case. If you look at the forces, the external forces at play, there are 2, gravity and radial GRF, and both of them are destabilizing, right? So gravity has a destabilizing torque, and the radial GRF doesn't really help you because it provides horizontal acceleration, so it's always trying to speed you up from the mid-stance position. And the bottom line is, if you do the math or numerical simulation, what you find is you're essentially stuck with the time scale of the inverted pendulum model, which is square root of R over G. It's very hard if you want uniform speed, which is how we walk, to go below that speed. So how can we help? For us, the simplest thing to do was to add a tangential restorative force, which is essentially going to fight against our tendency to fall. This is what gravity has been trying to do all our life. So we have this restoring force which can cancel some of that effect. And the simplest thing that we could think of to do this job, so we wanted a force which changes sign, because it always has to cancel gravity, or the effect of gravity. And the simplest term that you can think of just is a quadratic potential energy, where psi is now the angle between the body axis and the leg. So, you can think of it as a perturbative term. The first term in Taylor series expansion, whatever. Of course, this is a phenomenological model. So what this term does is, if you look at the evolution for the angle, essentially adds a linear restoring force that's seen here. And to illustrate mathematically, just to give you an intuition why this or how this works, we can look at the small angle limit. And so in that case, this can be recast in this form. And now you may start to recognize that this actually looks pretty similar to the inverted pendulum model, except for this prefactor over here, which has this cancellation. So it's as if this restoring force is slowing down gravity. It's by reducing the effective g to some smaller number. Okay? So that's its job. All right. So does this work? So we did the non-dimensional gait space analysis for AR slip, which now has just one extra parameter, this gamma A. These are now for two different angles, alpha equal to 11 and alpha equal to 25, that I've been using for this talk. And what you see here is if gamma A is 0, which is basically slip, it is challenged. Slip is challenged at the lower end. You barely can get to maybe the light yellow, which is over here. 0.05 or so, but then if you increase gamma appropriately, then you can get to really low numbers, these blue regions over here. And the same thing repeats even more dramatically if you go to largish angle like alpha 25 degree. A couple more visualizations of the same phenomena. So here we are plotting the minimum Froude number surface as a function of the angular spring and the alpha. And of course, if alpha is small, it's easy for an animal to get to low Froude numbers. That's what you see here. But the important thing for us is that if even for largish alpha, if you tune gamma appropriately, large enough, you can get to these blue or purple regions. This one is just a slice of this, one-dimensional slice to make a couple of points. So what you see here, so I'm now plotting again the range of Froude numbers as a function of gamma A. What you notice here is that if we want to walk slowly, we tune this gamma A, the animal tunes this gamma A, and this is like a critical value where it cancels most efficiently with gravity to give you a slow uniform walk. But if there is no gamma, obviously you get to this 0.05 value. So that's the conclusion that our non-dimensional analysis suggests, that we need AR slip. If we do, though, we should be able to explain slow walking motion and the horizontal ground reaction forces. So what does data tell us? So here is the data for a single human stance coming from George Mason lab. What you see is this classic, vertical GRF pattern of the twin peaks. They also have data for the horizontal GRF. And we are only focusing on this talk at the single stance phase, which is from here to here. And the main thing that kind of you immediately see is that both the models, so the green is our model, red is slip, does pretty well in reproducing the vertical GRF. Notice that this is 1,000. It is, the 0 is somewhere here. So it does really well. The uncertainty is really small. Whereas if you look at the horizontal GRF, that's not true. The green line hugs much more closely than the black line. And this is not a unique step that we found. It's actually pretty, essentially you see the same pattern repeating. So here we are plotting the RMS ratio between the slip versus our model. And you see a factor of, this is for the VGRF, it's close to 1. So that means they're more or less doing equally well. But if you look at the HGRF, it's a factor of 3, 6, or even 9. So just by adding one parameter, it improves the tracking the horizontal GRF enormously. Okay. All right. What about data from fruit fly? So Vikas's lab has done a remarkable job. I can't even imagine how they can get to this kind of precision with flies. If you look at the tracking, and we are able to model the fly trajectory, and you see that the horizontal part does pretty well, both the model, but the VGRF part, the horizontal part, there is some systematic difference, and in particular, what is absolutely blatant is if you look at the velocity profile. The velocity profile slip is absolutely horrible, but our model reproduces this inverted velocity profile where you have a maximum in the middle. All right, so since I'm almost out of time, let me just summarize by a couple of quick points. So far we have been looking at walking, but it seems it may be possible that even for running, the tangential horizontal force may be relevant. That comes with our model. This is a work which suggests that the VGRF does really well, slip does really well with VGRF, but not so much with the horizontal ground reaction forces. So to summarize, the AR slip is needed to better understand the horizontal ground reaction forces, which enable us to model slow uniform walk, as well as reproduce the opposite inverted velocity profile. There are lots of open questions, but I think I'm going to just flash this and leave it for questioning.
Questions? Aaron?
Maybe you said this and I missed it, but in the AR slip, there's a spring between the leg and the body. But usually in the slip model, the body doesn't have any angular state. So
Right.
what is it sort of pushing against on the other side?
So you have the springs which are connected, the leg is connected to the body via these angular springs. And the exact mechanism, so this is just a toy model to visualize the forces that are at play. You can have these springs so that the net torque, there is no net torque on the body, but there is an unbalanced force, unbalanced tangential force. And if you are thinking in terms of the external force that is acting on the body, essentially, we are always, for humans, we are always manipulating our legs to generate the friction and the normal force that we need for walking. So here, all we are saying is that the way we generate the normal and the friction force, it doesn't always align with the radial force, but there is a tangential component to it. On the other hand, for hexapods or quadrupeds, it could be a completely different mechanism to generate these forces because they have additional legs, which essentially gives you a tangential component.
We have another question right there.
So similar question to before, did I get that right, that there's no kind of underlying dynamic physical principle that generates this force? So it's basically a free parameter?
Yeah, it's basic. The way we are thinking is, so there are two issues, right? One is you generate a force from the ground. We are only getting forces from the ground and there is gravity. So that's one aspect of the story. And the second thing is, once you get a force from the ground, it's going to be transmitted to the body via the skeletal-muscular system. So I think there are two different points that we need to understand this. So the first one is, depending upon whether you're looking at hexapod or a biped like us, we are going to manipulate either the geometry or the way we press against the floor to generate a radial and a tangential force. That's our conjecture. And secondly, once we have generated this force, they are transmitted to our body by some muscular configuration, which can be very different and complicated. So if you're specifically interested in one sort of illustrative example, I can discuss that with you after the.
So we have a question there and then right there, if we can get a microphone back to her.
So I had a question about your model. I'll stand up.
Okay, sorry.
So I had a question about your the representation of the fly center of mass dynamics. So if you were to compare side by side the traces on the fly versus the human was much more consistent.
Right.
So is that average trace that you're showing actually representative of the behavior, or is there just a lot of variability from animal to animal, stride to stride?
That's a great question. Vikas, do you want to answer this?
I think we can't give you a very, very specific answer. I think that the most likely reason is that there is really a lot of variability from step to step. Mostly, and one would expect that because they have 6 legs, and the variability most likely comes from how you position those 3 legs in a tripod. Also, how the synchronicity of the tripods. The tripods are, the 3 legs of a tripod are not perfectly synchronous. All of those factors will lead to variability.
Thanks.
Okay, back there.
I have the same question as James.
Okay, I'll take your time then. I don't see any difference of fly walking when they walk on ground, on walls, on ceilings. At that scale, presumably their leg tips are essentially glued to the surface. So doesn't that suggest that this analysis is not really appropriate?
I'm not sure. I was with you the first part of the
If
story.
I'm upside down, gravity is doing something entirely different.
Right, but you would. I think what would happen is that if you look at naked eye, it may look similar, but when I'm absolutely sure that when you actually do record the data, you would see a difference. And note, there is another thing here. When the fly is inverted, clearly there is a gluing force, which is very different from the normal force that you get, right? So, for instance, at that time, the kind of muscles that you need to probably activate for that kind of walking could be different. The gammas that we find could be different. I think the main message of our talk is that we know that a force has 2 components, right? That's at least in the sagittal plane, there are 2 components. Why restrict ourselves to only one when just an addition of 1 parameter can do so much more? Now, so one has to look at other animals, one has to possibly look at running to see how general or how important the effect is. I imagine that when we go to faster gaits, the importance of this angular force would become less. But there is a lot of literature which actually does suggest that you have like initial push-off, like an initial acceleration and then a braking towards the second phase. So why not include that?
So tonight, let's have a bunch of beers and lie down and watch flies.
Thank you very much.
I'm